So I'll introduce Dr. Arvind Kumar Jha. Dr. Arvind Kumar Jha is currently working as Assistant Professor at the Department of Civil and Environmental Engineering, IIT Patna. He completed his MSc from IOETU, Nepal, and PhD from Indian Institute of Science, Bengaluru, in Geotechnical Engineering. His research interests include areas of soil stabilization, ground improvement, biogeotechnics, geoenvironmental engineering, and rock mechanics. Dr. Jha published more than 30 papers in various national and international journals. He is currently guiding 7 PhD students. He has over 10 years of professional experience, both academia and industries, in the field of geotechnical engineering. He has also received many prestigious awards from ISSMGE Foundation and NAST Nepal. So we welcome Dr. Arvind Kumar Jha. So incidentally, both chair and co-chair are of same guide students. Both of them were guided by Professor P.V. Shivapallaya at I.I.Sc Bangalore. So I'm very happy to introduce the both chair and co-chair. Now the floor is yours.
I invite the next speaker, a special lecture by Professor Bappaditya Manna of I.I.T. on the topic seismic response of concrete gravity dam foundation system or rock foundation with shear zone. Before you present, I would like to introduce briefly Professor Manna to the audience. Dr. Bappaditya Manna obtained MTech degree from IIT Kanpur in the year 2005 and PhD degree from IIT Kharagpur in the year 2009. He is presently working as Associate Professor in Geotechnical Engineering section at IIT Delhi. He has been involved in geotechnical research, consulting and education for more than 10 years. He is the author or co-author of more than 25 scientific papers in reputed journals and 70 papers in conferences. He already guided 5 PhD students and 36 MTech dissertations. He is a member of American Society of Civil Engineers, D Foundation Institute, Indian Geotechnical Society, and ISSMGE. His research interests are in the area of files under machine-induced vibration. So now I invite Professor Manna for delivering the lecture on seismic response of concrete gravity dam foundation system for rock foundation with shear zone. Over to Professor Manna.
Thank you, Professor Ramesh, for introducing me. So let me share my screen first. So I first thanks the organizing committee member of 7ICRAGE for giving me the opportunity to present the special lecture on seismic performance evaluation of concrete gravity dam on rock foundation system with shear zone. I'm Bappaditya Manna. I'm presently professor in Department of Civil Engineering, IIT Delhi. So basically, this work which I'm presenting is a part of a consulting work which IIT Delhi has taken up. So you know basically that the hydropower project. So in India, so we have a basically lot of potential site where the hydropower project or hydropower dam has been constructed. So India basically ranks 6th in the hydropower production in the world. And if you see in this slide, so you can see that basically different location has been identified as a potential location for the hydropower dam. But if you see that developed part is very limited, even for the northeastern part, we have a huge potential of the hydropower generation. But there are certain issues for which we cannot implement it as per our expectation. So basically, the construction of a dam is basically the backbone of any hydropower development, and it having some less carbon footprint. So basically, this hydropower dam is not only for the production of the power; it also used for the different other purpose like flood control, irrigation, water storage, and tourism, so on. So now, if you see the problem of the dam foundation, it happens because there are lot of uncertainties involved in the properties of the rock which exist and which is identified as the potential site. So because the dam is a massive structure and it developed the high stresses in the foundation due to the large load imposed by the dam body itself. And it has been found that the 20% of the failure cases happen due to the foundation failure due to the excessive load of the concrete dams. So therefore, the most problem which we found that the interaction, soil structure interaction with the dam and the rock foundation, due to the troublesome geometry, which therefore needs for the greater attention. And we need to understand that if there is some joint which is filled with some clay material, or if there is some shear seam exist at the site, so how to build a dam foundation with proper design. So therefore, this kind of similar problem arises one certain location. So I'm not here saying the location because of the NDA agreement between IIT and the client. So here there is one site which is proposed for the hydroelectric project of about 1200 megawatt power, and we have found that the right bank of the site, basically there is a huge rock slope failure happen, and therefore this part was become very unstable, and therefore cutting of the slope was not possible, because whenever we are cutting the toe, that all the slopes start failing. And you understand there is a huge mass. If this kind of failure happen, I mean the whole thing will be just crushed away. So therefore, the client approaches us and they told that that this 1 to 13 has been proposed. These are the 13 different the segment of the dam, and out of which 1 to 11, 12, and 13. These are the exist on the left and the right part of the slope, and which is okay. But whereas in the 8, 9, and 10, you see there is some lot of weathered rock was there, and if you start cutting here, and you may reach to the parent rock or the foundation rock. But the problem was that when you start cutting this part, the whole thing may get collapsed on the right back. So therefore, there was an issue that how to tackle this problem and what is the possible solution for that. So the 5, 6, 7 that was, and 3, 4 that is also okay, because it reached up to the foundation grade rock. So the construction can be done and excavation happen. So the challenges arises here for the block 8, 9, and the 10, where you can see that these are a lot of the loose material exist, and you can't cut it because there will be the right bank slope will be unstable for that. So therefore, you can see the side location where you can see this is the location of the block 8, 9, 7, 8, and 9. Here this is the block 7, 6, 3, 5. There was no issue, but here there is a issue because you can't excavate further to reach up to the parent rock or the foundation rock, because otherwise the right bank will be collapsed. So, and one more challenges was there that during the the soil investigation or the ground investigation, it has been observed that there is the shear zone exists at the exposed cut slope, and it has been just lying below between the blocks 6, 7, 8, and 9, and which having a thickness of around 8 meters. So therefore, they suggested to not to excavate further, and we need to first take care of the shear seam and also the loose soil. So there are two things here. One is that we should not cut further because there is some collapse of the right bank, and also we need to take care of the shear seam exists below the foundation. So therefore, they suddenly come up with some solution that why can't you place the piles? So piles at a certain block number. So therefore, they placed here at the 8 and 9 that they place the pile foundation there, so that they're expecting that the maximum load from the superstructure, that means from the dam, can be transferred to the parent rock or the bedrock, so that they can avoid the stresses of the load on the shear seam. So that is basically kind of the load transfer they are expecting, that okay, why can't you place this foundation and you build a dam at the various blocks. So now that the client approaches IIT Delhi, so we find out the design philosophy first. So that is as per this IS code. So IS 6512 is very well established code for the design of the solid gravity dam. So there are 7 load combinations up there. So load combination A saying it's a self weight of the dam, then load B, dam weight and the water pressure, and C is the dam with the water pressure and the maximum tailwater level and considering the uplift. So here C and the D and E is the combination of the A and the earthquake. And here I am talking about this part because this basically the conference is more inclined to the earthquake. So here I will see that how we can take care of the load combination A with the earthquake and load combination B with the earthquake, and how the result, whether it is going in the favor of the design or we need to go for some modification, that I will be showing you. And another thing that the earthquake analysis has been done with the two cases, that is one with the pseudostatic analysis, one is the site specific seismic data. So here this is the just a standard procedure which is there in the software called finite element software called Plaxis. We considered the Princeton model in 2D. So this is the concrete wrap. There is some wrap below there, and the wrap there is a certain portion we are providing the pile foundation which passes through the shear zone and the weathered rock. And here you can see on the left part there is some fresh rock available. So this is very standard procedure, that creating some geometry, then we can generate the mesh, define some initial condition, then there is some stage construction as per the site construction process, then run the analysis and check the result. So here this is basically the site map, and as per the same geometry and the material property, whatever is available, we try to simulate, replicate the same thing in the Plaxis. And here I'm just showing you some steps basically which we follow. So this is basically, you can see the wrap dam, and we introduce the wave load, and this is the dam body. Here is the backfill material. Here you can see this is the weathered rock. There is some shear zone, pile groove, and there is some wrap and hydrostatic pressure and the fresh rock. So this is a standard, standard boundary condition. We consider the bottom fixed, and at the side there is some X fixed and the Y free. So this is very standard thing, we got it. And as far as the modeling part is concerned, we consider the soil and the rock with the 15-noded triangular element with the cluster features, and dam body is considered to be a 15-noded triangular element with polygon cluster feature. Wrap is modeled with the plate features, and similarly for the pile with plate feature, considering the effect of the spacing in the plane stem. And the interface we are considering to be the rigid element. That means it's a rigid contact between the dam and the foundation soil. So these are the various soil and the rock properties, and that is based on the soil investigation data obtained from the site. So basically there are four major components. One is the fresh rock, weathered rock, and shear zone, though it's a big question mark that how accurately we can get the properties of the shear zone, overburden, and the backfill material. So these are the properties we obtained. And the dam parameter has been taken. So basically we take the parameter corresponding to the M15. So this are the property has been taken, and the PCC has been done with the M25 concrete. So these are very standard properties has been taken, and these are the standard process. First create the mesh generate, and with considering the element with the fine and the coarseness factor varying from 0.25 to 1. And initial condition, first apply the gravity loading to generate the institute stress. The stage condition, that means first filled with the PCC up to the foundation level. And the second stage is the casting of the pile. And thereafter we cast the wrap. And then, we apply the load of the, dam. Dam is basically constructed here, and which is placed on the wrap pile foundation system. So in the first case, there is no tailwater is considered. And then in the stage 5, we consider the full reservoir elevation, and there is no tailwater on the downstream side, and we consider the normal uplift pressure. And the stage 6 is basically the reservoir at the maximum level, and all tailgates are open, a normal uplift condition. And stage 7 is the combination of A and the earthquake. And similarly, F is the combination of B with the earthquake. And this is basically just a combination as per given in the IS code, that all the drainage holes are the inoperative, that is for the maximum uplift condition. And similarly, the load G is the combination with E, but with the extreme uplift. So all combinations has been considered in the analysis. So here I'm just telling you that how to get the parameter for the seismic condition and what are the various type of result we obtain. So as per IS 1893, that site belongs to the zone 5. So we consider the seismic zone factor as per the zone 5, that is 0.36. So our horizontal acceleration coefficient has been taken 0.36 g, and vertical acceleration coefficient is 0.24 g. So that has been given as an input to the praxis. And the second analysis is based on the site-specific seismic design parameter. So site-specific study has been done, and this is, you can see the correlation of the epicenter of the first wave with the major tectonic movement. And here you can see the different location of the fault and the gravity fault and the thrust fault, shear zone, and there is some project site has been located here, and the various magnitude has been also indicated in this map. So based on that, the seismologist gives us two values. One is design basis earthquake time acceleration history in the horizontal direction and the vertical direction. So here, based on that, you can see basically the peak current acceleration for the horizontal is 0.316 g, and whereas vertical case is 0.206 g. So we apply both the cases in the praxis model, and we try to see that how the dam and the foundation system. Yeah. So we have taken the different point here, and here we found that at the top, that is at the point C, we have seen that it rotates maximum, that is 2 or 3 times the input acceleration history. So these are the different typical result of the analysis. Deformed mesh, dam displacement, principal stress, and the deviatoric stress. So what we found that maximum compressive stress is just exceeding the allowable compressive stress at certain location, that is at the toe and the hill level, and other part that is okay. And whereas similarly for your dam founding layer at the P6 level, it also exceeded near the hill and the toe region, but other part remaining the stable, that is within the permissible limit. Similarly, at the rock foundation, it has been found it is less than the allowable peak rock mass compressive stress. So if you see the behavior of the structural member, that is wrap and the pile group, you can see the settlement response, you can see the axial forces and the bending moment on the pile. And this is the shear forces of the pile that is required for the calculation of the reinforcement. That is not the concern of the geotechnical engineering, but we pass on all the information to the structural engineer. So this is the bending moment and the wrap and the shear forces of the wrap. This is very standard thing. So what we can found as a geotechnical engineer, that pile axial force, that is well within the permissible limit, because the allowable vertical pile we found that is around 4,000 tons, which is much less than that. And maximum settlement is coming up to 43 mm, and the allowable is 50 mm. Because if you see the latest code IS 16700, that is the criteria for the structural safety of the all structured building. So it has been recommended 50 mm. But if you go by the IS 2911 part 4, it's saying 25. But there is no code specified that what to take for the dam foundation. Therefore, we adopt that why not to take for the tall storage what the wrap pile foundation has been recommended. So we go out with the 50 mm settlement. So that is within the permissible limit. Similarly, you can see the settlement of the wrap, that is also within the permissible limit, but no maximum differential settlement criteria is given for the dam. But yes, this is almost very negligible. So 1/3 and 3,500 is quite less. And we have also compared with the pseudostatic analysis with the time history analysis. So we can see that they are mostly talking to each other, not much difference, except for the pile load, where you can see it's almost double that maximum axial load on the single pile. So, but still, I mean, with the time history, that load which you get from the single pile, that is less than the safe, load carrying capacity of the pile. So final recommendation. Yes, sir. Just one slide. So final recommendation was there. Yes, we can reinforce the zone with the PCC field below the dam, and we can recommend the RCC below the upstream site, where we are getting a very localized stress concentration. So therefore, this has been recommended finally. And I would like to add the challenges. The challenges is that to get the site-specific seismic design parameter, because that is the key parameter from which the entire thing is dependent. And the dynamic properties of the soil and rock, particularly joints and shear seams. And we need to understand the boundary condition, and for which you need to give a lot of trials for that. And obviously, this kind of analysis needs a lot of computational time. So we have to, it's not very suitable for the industrial problem because the time is very limited there. So I will just conclude here. Thank you very much for this opportunity, and Any question? Thank you.
Thank you, Professor Manna. Any questions from the audience? Please post it.
Yeah, can I have one question?
Sure, sir.
Professor Manna, very interesting study. I have one question. When you designed the piles, did you consider any load because of that shear zone, lateral force?
No, actually, see, I mean, it's a finite element model. So
Yeah.
we are not introducing any kind of lateral forces there, because, but where we have found that it is there, because
Yeah.
we have found that at the interface of the shear zone and the intact rock, the moment is maximum. So there we are expecting that bending moment is maximum, means there is some lateral displacement happen. So
Yeah.
there is coming. So basically we pass on this information to the structural engineer. They need to put the reinforcement accordingly to take care of bending moment.
Okay. Thank you.
Thank you. Any more questions? If there are no questions, I'll go. Thank you, Professor Manna, for your excellent lecture.
Thank you very much, sir.